Welcome to The Explainer. What if I told you that a concept at the very heart of modern math, infinity, might be built on a giant mistake? Today, we're diving into a source that makes that exact radical claim. I mean, just look at this quote. We're talking about a source that calls one of the most celebrated proofs in all of mathematics weak and dishonest. It's an argument that a core idea, one that's been accepted for over 100 years, is just fundamentally wrong. And that's really the central question posed by our source, the writer Miles Mathis. He's challenging the very foundation of how we think about infinity. So get ready, because we're about to question some really long-held beliefs in the world of math. Okay, so before we can understand the challenge, we first have to get a handle on the idea being challenged, right? So let's do a quick recap of George Cantor's famous proof about infinity. This has been the standard way of thinking for over a century. For a very long time now, the accepted wisdom has been that some infinities are actually bigger than other infinities. Yeah, I know it sounds weird. Specifically, Cantor proved that the set of real numbers, that's all the numbers, including decimals that go on forever like pi, is a larger infinity than the set of simple counting numbers, 1, 2, 3, 4, and so on. So how did he do it? Well, this slide shows you the setup for his famous diagonal proof. Just imagine for a second that you could create a perfect, complete list of every single real number. On the left, you've got your counting numbers, 1, 2, 3, and on the right, you pair each one up with a unique real number. Now here comes the clever part. You look at the digits that form a diagonal line down the list. Then you create a brand new number by changing every single one of those digits. So if the first diagonal digit is a 1, you make yours a 2. If the second is a 2, you make yours a 3. You get the idea. This new number you just made is guaranteed not to be on your original list because it's different from every single number on there in at least one spot. And the stunning conclusion? Your supposedly complete list was never complete at all, which means there must be more real numbers than counting numbers. And right here, this is the exact point where our source, Miles Mathis, slams on the brakes. He says the whole proof is based on a faulty premise. This idea that you could even hypothetically start to write down an ordered, complete list of all real numbers. He argues that's just impossible from the get-go. So, according to Mathis, this isn't just a tiny error. This initial flaw is the seed for a much bigger problem. The Cantor's entire proof is really just a classic logical fallacy, what's known as a straw man argument. C. Cantor is using a technique called proof by contradiction. It's a pretty standard move. You start by assuming the thing you want to disprove is actually true. So Cantor starts by saying, okay, let's assume the real numbers are countable, just like integers. His goal is to show that this idea leads to an absurd conclusion. Mathis says the fatal flaw is right there in step 2, the straw man. He argues that saying a set is countable in theory doesn't mean that a real person can physically write down a finished list of it. That requirement, he says, is the straw man. It's an impossible standard that Cantor just invented so he could then triumphantly knock it down. So the takeaway from this source is that Cantor isn't defeating a real argument. He's defeating a ridiculous, impossible requirement that no one would ever seriously defend. And if your starting point is a fantasy, well, the proof that follows from it can't be much better. And this critique, it doesn't just stop with Cantor's proof. Oh no, it expands and forces us to challenge our basic understanding of the number line itself. The one we all learned about in school. This slide nails the disagreement perfectly. So on the left, you've got the standard view. The line of rational numbers, that's any number you can write as a fraction, is full of tiny little holes. And those holes are where the irrational numbers, like pi or the square root of 2, fit in. But then on the right, you have Mathis's argument, nope. The rational line is already infinitely packed. It's totally continuous. There are no gaps to fill. Okay, so if there aren't any gaps, where do the irrational numbers go? Well, Mathis puts forward a pretty wild idea. He says they don't squeeze in next to the rational numbers. Instead, he thinks of the rationals and the irrationals as two totally separate, complete number lines. And at the abstract level of infinity, they exist as perfect overlays, like two transparent sheets laid right on top of each other, mapping perfectly one-to-one. And if that's true, it means they have to be the same size of infinity. Now, if you follow this train of thought to its final destination, you end up with a complete and total rejection of what's called transfinite mathematics, the whole branch of math that deals with going beyond infinity. And a famous old thought experiment really highlights the problem. Ah, yes, Hilbert's Hotel. You've probably heard this one. Imagine a hotel that has an infinite number of rooms, and every single one is occupied. The classic riddle is, what do you do when a new guest shows up looking for a room at this completely full yet infinite hotel? Well, Mathis just slices right through that paradox with this dead simple statement. He says the whole question is a logical contradiction from the start. If the hotel is infinitely full, it is by definition complete. There can't be a new guest because a complete set already contains everything. And this really is the heart of the whole critique. The very idea of going beyond infinity, the transfinite, is, according to this source, a basic mistake in logic. You can't just add one to a set that, by its very definition, already includes everything. For Mathis, infinity means complete, full stop, the end. And here's where the argument escalates beyond just math and becomes this sweeping cultural critique. Mathis is basically claiming that accepting these paradoxes isn't a sign of being smart, but is actually a symptom of a kind of intellectual decay that has infected modern thinking. So we're left with this really provocative question. Is it possible that what we all accept as a fundamental mathematical truth is actually built on a shaky foundation? This source certainly thinks so. It really forces you to ask, is infinity this complex, beautiful ladder of ever bigger sizes, or is it something way simpler and far more final? The debate proves that even in math, maybe nothing should be off limits to questioning.